Welcome to this Prism DVD. Prism, it was a 3-year technology programme supported by the Technology Strategy Board, and the aims of the project were to look at incorporating electrical sensors into composite materials, this for the purpose of structural health monitoring. Structures and applications such as bridges, wind turbines, boats and subsea vessels are just some of the many areas where this technology could be considered.
I'm Julian Ellis of Ellis Developments. As a company, we're always interested in developing new technology because we're a technology development company primarily, and the incorporation of sensors into composites was quite interesting and blended in with the technology we've developed for fibre placement techniques. Once we'd planned the project through and written a proposal, it was submitted to what is now the Technology Strategy Board. The proposal was for something in the region of £1 million and has been a 39-month project. When Kinetic realised they had some interesting technology on electrical sensors for composite materials and wanted a consortium to help develop those techniques, they contacted a number of companies, most of whom had collaborated with Kinetic in the past at some stage, and we held a meeting and thrashed out ideas. A number of those companies that attended that meeting inevitably dropped out, and we began to put forward a proposal to what is now the Technology Strategy Board, and that was accepted, and the project started in late 2005.
I'm Steve Phillipson, Business Development Manager of Sigmatex and the project leader for Prism. Sigmatex, it's a world leader in the manufacture of carbon fibre fabrics, and it converts fibre into woven, unidirectional, multi-axial and 3-dimensional fabrics. It also has the ability to powder coat fabrics. Sigmatex has many state-of-the-art technologies, some of which are the very first of their kind to convert carbon fibre into a fabric. Several of these technologies were used and contributed to the success of the Prism project. Over the next 20 minutes, the project partners, namely Sigmatex, Ellis Developments, Kinetic, Deep Sea Engineering and BVT, will each take you through some of the work that they've done during this 3-year project. We hope you find the content interesting.
My name is Andrew Ball. I work for Sigmatex UK Limited in the technical department. I'm a lead development engineer with responsibilities for multi-axial fabrics. My role within the Prism project was to interpret the designs and requirements required by the partners for the baseline fabrics, and therein the incorporation of the sensing material into those fabrics. The fund came with the incorporation of the sensing material. Sigmatex has had a lot of experience in putting other materials into a carbon matrix, from SMA wires through to other specialist fibres. The sensing material sort of took that a step further. The first material selected by Work Package 1 Kinetic was an amorphous ribbon. This was quite fine and very sharp, which gave its own problems, but we overcame these.
Our technology allows us to place fibres in any position that is required by an engineer, and therefore it is an appropriate technology to use for sensor placement where the engineer's specifications may require sensors to be placed in unusual or non-straight line configurations, and the embroidery technology that we've developed and other stitching techniques mean that we can place the sensors wherever they're required.
My name's Lisa Fixter. I work at Kinetic in the Smart Materials group. I'm based in the Aerostructures group, which is part of aerospace. I've been working on smart materials and particularly structural health monitoring sensors for about the last 10-15 years. Kinetic provides research, technical advice and technical solutions and services to customers in core market defence and security. We operate in the UK, North America and have recently entered into the Australian defence consultancy market. Kinetic's involvement in the Prism project has essentially been twofold. We've been looking at the sensing side of things, and then we've also been looking at the manufacturing of the preforms and the fabrics, which has involved stitching robots. So going back to the sensors, Kinetic's main job essentially was to scope technologies out there and do a state-of-the-art review and come up with long-line sensors that could be incorporated for preforming, weaving, stitching with and stitching in position. So as a result of the state-of-the-art review, we took forward amorphous sensors and piezo-coax sensors, and then we characterised the sensors, looked at their response to strain, stress and impact events, and then we had to scale up then to demonstrator components, the predominant one being the bridge component, of which Kinetic was involved with embedding the sensors, connecting to them, and then post-production we've had to analyse the sensors and see what their performance is like being scaled up to a large structure. This is the final demonstrator, which is the bridge test component, which has embedded piezo-coax sensors and amorphous sensors. I'll just explain how some of the sensors on the Prism project were incorporated into the bridge demonstrator. We used piezo-coax, which was incorporated into the top skin, and it was incorporated using two methods. Sigmatech wove the piezo-coax cable into one ply of the carbon cloth, and that was incorporated as a ply on the top skin, and then Kinetic stitched in a pocket piezo-coax between the top two plies. So there's actually two methods of incorporating piezo-coax into the top skin of this bridge component. We've used the piezo-coax in its bare forms without the outer insulation on, so we're actually using the carbon composite material as the outer electrode and testing it dynamically and seeing how it responds to an impact event. The other sensor type that's been included on this bridge component is amorphous ribbon, and as you can see on the top surface here, you can see a naught orientated sensor and a 90-degree orientated sensor that's been stitched into position. The two layers are independent, stitched on glass fabric that was actually included and infused as part of the main composite bridge component.
In the early stages of the project, Kinetic assessed which sensor types to use and found two main sensor types which are useful for embedded sensors in composite structures. The first one being this amorphous sensor, and this is an amorphous metal alloy which is available in a ribbon form or wire form, commercially available in very long lengths, and it's quite cheap. The other sensor we have is a piezoelectric wire sensor. And this is a piezoelectric material which, when you strain it, you develop a charge on the material, and you can use some electronics to exploit that and use that as a sensor. Here's a more flexible beam that we've got instrumented with embedded sensors, and by looking at the oscilloscope screen, we can see the output of the sensor circuitry and giving us a linear output when we apply strain to the component. So you see it's very sensitive.
I'm Robert West. I work at the Aerostructures group within Kinetic, where I look after the stitching robot. This equipment has been used all the way through the Prism project for the location and positioning of the sensors within the composite preform structures. The Kinetic robotic stitching facility allows 3D shaped components to be produced in textile technology. We can put in 3 different types of stitch. We can tuft, we can put in blind stitch, and we have a special composite 2-needle stitching technique. These have all been tried out and used within the Prism project. Most commonly, we've been tufting sensors in to allow high densities and precise placement of the sensors. The long line piezoelectric sensors were trapped in pockets formed by blind stitching, and this has worked effectively, and we can see the results in the bridge demonstrator that's been made. The tufting technique has also been used to apply the glass sensor layer onto the face of the Prism bridge demonstrator. This has allowed essentially a preform to be produced so that we can minimise the work downstream within the laminating partners. The preform can be taken straight out of the packet, as it were, and transferred straight to an RTM or resin fusion facility. Preforms are required for low-cost composite production. They avoid the whole need for pre-breaks and expensive autoclave, allowing low-cost resin infusion techniques to become very much more controlled.
The amorphous ribbon sensor was selected for modelling analysis by DeepC. So DeepC took the ribbon and incorporated it into both sort of flat panel coupon specimens and filament wound specimens. So they, from the sort of structural side and mechanical properties, the model looked at seeing if there was a reduction in strengths on including amorphous ribbon in composite materials. BVT actually validated mechanically with the models. Kinetic also produced filament wound tubes, positioning the sensors to which their model dictated their position, and this was done successfully on their filament wound machinery.
DeepC is a leading engineering company which provides services of engineering and management to the oil and gas industries. Our specialities is the concept and detailed design of subsea structures, flow lines, risers, and review of existing design and fields. Hello, my name is Hamadi Abishu and I am Senior Project Engineer of R&D Research and Development. Our area of expertise are the modeling and the detailed design of the offshore high complicated problems, going from the wellhead production to the end facilities of the field.
And in this Prism project, we focused on the development of numerical models to assess the influence of the mechanical properties.
Hi, I'm Naveen Ravirala, working in DeepC as a project engineer. We are the precursor to the manufacturing sector. We provide the design, structural health monitoring of the system. Our expertise are in the numerical modeling. We strongly believe the Prism project will open new applications into the subsea structures and oil and gas industry as well. And the new monitoring technologies, such as the one which are involved in the Prism project, the embedded sensors into the composite, should actually give open new applications into the composite phase. And this will mean that we provide the assurance to the client with a new material and technology in the applications leading into the subsea structures.
My name's Ed Finden. I work for BVT Surface Fleet We're a joint venture between VT Shipbuilding and BAE Surface Fleet. We were formed middle of last year to be the #1 supplier of ships to the UK MOD. My role within the BVT Surface Fleet Group is I work for CTC, which is the Composite Technology Centre, which specialises in project managing the composite projects within the group, both from an R&D perspective and for a productionising and project managing point of view. I've been with the group for 5 years now. Before that I was project managing also in the composites business in the marine industry, boat building, of which I've been doing for the last 20 years, really since leaving education. My role within the CTC group, or the CTC department, is really twofold. The first element of my job, as I mentioned, is project managing the commercial projects within the group from a planning point of view, materials, specification, design, and making sure that the products that we get involved with are built on time and to budget to specification. That's quite an interesting part of my job, as it involves all parts of the manufacturing process, from the initial design concepts through to delivering the final products and putting them on trial and test. We were approached by Kinetic about 5 years ago to get involved with another TSB or DTI funded programme. At that time it wasn't known as Prism, it was just known as a new project. We were very interested to get involved, as we always have been, because we've got this history of being involved in R&D. We really see the value of it. So I suppose the main contribution we've made to the programme is the manufacturing side of it. That's really our expertise. That's what we've done historically in these programmes, as well as add guidance and design input in the early stages, but really manufacturing is our strong suit. We've got a history here of R&D programmes probably dating back 20 years, and these have ranged from the Dera plastic tank, which was a very thick e-glass vinyl ester infused fighting armoured vehicle in the days before Kinetic, through to some resin infusion and RTM work for some well-known UK defence contractors. In the last year we really focused down on the application case, the bridge section, which would be the cornerstone of the project and from my point of view, the real deliverable. The reports are great, very important. Mechanical properties are crucial for the engineering of these structures, but actually, could it translate to a real product? The material came from Sigmatex after Kinetic did a numerous amount of tests to check the sensitivity of the technology that we put in, check the robustness of the connections, because they're always a tricky point in this type of research program or this type of technology. And when they were happy, we were happy, and we specified the bridge. Deep Sea did the structural engineering, and an interesting thing happened in the sense of Kinetic, who were adding all the sensing technology, got a lot of the material from Sigmatex and from ourselves. Ellis fed in some of their stitching of the sensings. I think the 3D arrays were supplied by Ellis. They also went to Kinetic, and Kinetic stitched together the outer skin and inner skin of the bridge demonstrator in one stack and delivered it to us in a pizza box, a very big pizza box of 1.5 metres by 4 metres long. But nonetheless, all we had to do was take this preformed bridge section, dry bridge section, out of the pizza box, slide it onto our infusion table, build the sides around it, bag it up, define the infusion strategy, which we've done through the 90 test panels we've made through the 3 years, and infuse the components. So it was actually fairly straightforward to make the demonstrator because of all of the technology that had been incorporated and preformed by Kinetic and Ellis. So I think we learnt an awful lot just from that one element of the programme. Forget the sensing technology, the preforming went very well. Of course, we had to convince ourselves that we could infuse fairly thick sensed skins that were pre-stitched together either side of a foam core, but we were sort of comfortable that we could do that, although that day and night that I infused it I was a little bit anxious, because it's always the critical time for us in the manufacturing. I was recently at a meeting with one of our primary customers on the 5 to 10 year future of naval ships, and a lot of what we were talking about was multifunctional materials, smart materials, reduced maintenance, reduced through life costs, and these are all of the elements that Prism gives you. So we're very, very hopeful. We think that this is exactly aligned to what our customers demand. Often we don't have a very clear picture of how these structures are actually being loaded in real life. We have an indication, we have an idea, but no one's, as far as my knowledge goes, have actually ascertained the real life loads, except when there's a problem, except when there's catastrophic failure, when you can do retrospective engineering, retro-engineering, and find out what the loads were. In terms of medium to long-term future, I can realistically see many high-value, large composite components that we make incorporating this type of technology as a norm, not just a one-off, not just a special, but actually driving the costs down, pushing the reliability up so much.
The applications for the Prism technology are quite widespread. A simple example is an aircraft fuselage. In commercial aircraft, a number of service vehicles attend to the aircraft during its stay on the ground, and if a vehicle strikes the aircraft, it can cause damage that in a composite aircraft can't be seen. Therefore, a number of aircraft builders and users are very wary of the composite structure, despite the benefits of very low weight and hence a cost operating advantage. If one incorporates sensors into the body and the wall of the fuselage, if a vehicle strikes the fuselage, the position and the strength of the strike to the fuselage can easily be measured, because it's a continuous measurement technique, and therefore safety of the aircraft frame can be guaranteed.
The partners and I hope you found this technology of interest, and should you wish to discuss further, please don't hesitate to make contact with any one of the participants. Our contact details can be found on the cover of this DVD, and we look forward to hearing from you. And thank you for watching.